Okay, let's dive in. You've probably wondered, like we all have, just how much do these large language models really know? Is it, actual understanding, or are they just unbelievably good at remembering all that data they ingested during training? It feels
Yeah.
like such a basic question, right?
It absolutely is. And figuring out how to separate true understanding, what we call generalization, from just sort of rote memorization of specific data points, that's been a huge challenge. Most ways people tried before, well, they struggled to draw a really clear line you could measure.
Exactly. But now we've got this really interesting new research paper, and they propose a completely new way to actually measure it, to quantify how much a model memorizes about its training data, down to the bit, apparently.
That's right. So this deep dive, it's all about unpacking what they found. We're going to look at how they define memorization differently, how they use that to estimate like the storage capacity of a model, what happens when you train models on, real text versus just random noise, and crucially, how this ties into things we see, like that weird double descent effect, and how well privacy attacks actually work.
Yeah, so our mission is simple. Help you cut through the jargon, get these core ideas, and really understand what matters about how these models store and use information. So first things first, this new definition of memorization. Let's unpack that.
Okay, so the main problem they're tackling is separating information about one specific training example, that's what they call true memorization, from information about the overall patterns in the data, generalization.
Right. Like if the model knows Paris is the capital of France, did it just memorize that exact factoid because it saw it a million times? Or did it learn a general concept like countries have capitals and can apply it?
Precisely. Or if it spits out a sentence word for word from its training data, is that just pure recall? Or is it generating something highly probable that just happens to match something it saw? It's tricky.
Yeah.
So the paper tackles this using information theory. They talk about it in terms of compression rate or information content measured in bits.
Okay, hang on. Compression. How does compressing data tell you if a model memorized something?
Okay, think of it like this. You've got a sentence, right? The quick brown fox, you know the one. How many bits does it take to describe that sentence from scratch?
Okay.
Now, how many bits would you need to describe that same sentence if you could use the trained language model as, like, a reference point? If the model knows that specific sentence so well from its training data that it can help you describe it way more efficiently using far fewer bits well, then the model has memorized specific information about that sentence.
Ah, I get it. So the model is like a specialized compression tool, a zip file, but only for the specific things it remembers really well from training. The better it compresses something because it saw it before, the more it's considered memorized.
Exactly. And they use this idea to formally separate two things. One is unintended memorization. That's the information specific to the training data set it saw. The other is generalization information about the underlying patterns, the sort of true data source.
And why is making this split, using this compression idea, so useful?
Well, first, it works at the sample level. You can measure memorization for each individual piece of data. Plus, it doesn't depend on how the model was trained, which is good because often we only get the final model. And most importantly, it really tries to isolate that dataset-specific remembering. It uses some...
Okay, so they have a method, a principled way, to say for this specific sentence, the model stored, say, X bits of information just about that sentence because it was in the training set.
That's the idea, yeah. And once they have this measure of unintended memorization for individual samples, they use it to estimate something really fundamental: the model's maximum storage capacity. How much specific stuff can it actually hold?
Right, the capacity. How do they measure that?
This is pretty clever. They train models, but instead of text, they feed them completely random bit strings. Just like pure noise, uniformly sampled bits.
Random data. Why?
Because in truly random data, there are no patterns, no structure at all. So generalization is impossible. There's nothing to generalize. Any information the model manages to retain about that random data has to be pure memorization of the specific random bits it was shown.
Ah, okay. So by training it on pure chaos, they isolate its raw memory limit.
Exactly. And what they found is pretty striking. These GPT-style models show a really consistent capacity limit when you measure it this way.
Okay, don't leave me hanging. What's the number? How many bits can a parameter actually store?
The estimates cluster around 3.5 to 4 bits per parameter. Specifically, they found about 3.6 bits per parameter for models using half-precision numbers, like bfloat16. And it's a bit higher, maybe 3.83 bits per parameter if you use full FP32 precision during training.
Wow, that's specific. And they show this visually, right? I think I saw the charts.
Yeah, figures 1 and 6 in the paper. They show that as you train on more and more random data, the total measure memorization climbs up and then just plateaus, hits a ceiling, it hits that capacity limit, and feeding it more random data doesn't increase the total memorization. The memory banks are full,
You
essentially.
just can't cram any more random facts in.
Right. And they also found this capacity scales pretty much linearly with the number of parameters. Bigger model, proportionally bigger memory for specifics.
Okay. Okay, so that's the limit for random noise. But, models aren't trained on noise. They see real text,
Yeah.
language, where patterns are everything and generalization is the goal.
Yeah.
So what happens then?
Right, that's the crucial next step. They apply the same framework, the same measurement technique, but now to models trained on actual text, like the FineWeb dataset, where generalization can happen and you want it to happen.
But how do they separate the memorization of a specific sentence
Mm.
from just like knowing grammar or common phrases when both are going on?
That's a good question. They use a reference model. It could be a much larger model, sort of like an oracle, or maybe a model trained on the entire dataset. By comparing how well the model you're testing compresses a data point versus how well this bigger reference model compresses it, they can sort of subtract out the general language knowledge and isolate the compression boost coming from remembering that specific sample. It's figure 2 in the paper.
Got it. It's like finding the extra compression due to specific recall. So what's the dynamic they observe when training on real text?
While the unintended memorization of individual text samples, it still goes up as the dataset size increases, just like with random data. It heads towards that capacity limit. But then something really interesting happens.
Ah, the trade-off you mentioned earlier.
Exactly. As the models start to get good at generalizing, you see this when their loss on unseen evaluation data starts to drop. The amount of unintended memorization for individual training samples actually starts to decrease. You can see this in figure 4.
It goes down. Wait, so getting better at generalizing makes it remember less specific stuff.
It seems so. The model starts learning reusable patterns, right? Rules of grammar, common phrases, concepts. And once it learns those general patterns, it doesn't need to waste its limited capacity remembering every single specific example of that pattern. It consolidates. Wow, that sounds like it maps perfectly onto that double descent thing people have seen.
It fits beautifully. Yeah, double descent, that weird phenomenon where a model's test performance first gets worse, then actually gets better again as you make the model bigger or give it more data past a certain point.
Yeah, it's totally counterintuitive. You'd think more data, bigger model, always better performance, right? Not this dip in recovery. Well, this paper offers a really compelling explanation. Look at figure 3. Their experiments show that the dip and subsequent recovery and test loss, the double descent, happens right around the point where the size of the training dataset starts to exceed the model's estimated memory capacity.
Whoa. Seriously. Right when it runs out of room to just memorize everything.
That's the hypothesis, yeah. Once the model literally can't store every single data point individually because it's hit its capacity limit, the training process essentially forces it to find more efficient representations. It has to find those general, compressible patterns that cover lots of examples instead of just memorizing specifics. And that shift from prioritizing memorization to prioritizing generalization because it has to leads to better performance on unseen data. That's the second descent.
That is such a neat explanation. It connects the physical limits of the model, its parameters, its capacity directly to these weird training dynamics we observe.
It really does connect the dots between memory and performance. And speaking of connecting dots, they also looked at what this means for privacy, specifically for things like membership inference attacks and data extraction.
Right. Membership inference trying to figure out if one specific piece of data, like my personal email, was in the training set. And extraction trying to actually get the model to spit out chunks of training data.
Correct. They used their framework, their measure of memorization, to see how it relates to the success of these attacks.
Okay. And what did they find? Is one harder than the other?
Generally, yes. They found membership inference seems to be easier than extraction. That's in figure 11. It takes less sort of leakage for the model to reveal that it saw something compared to getting it to reproduce it perfectly.
That makes intuitive sense, I guess. A hint versus the whole answer.
Yeah. But what's really cool is they developed a scaling law. You can see it in Figure 8 and Figure 18. It predicts how successful a membership inference attack is likely to be. They use the F1 score to measure success based purely on the model's capacity and the size of the data set it was trained on.
Wow, like a formula for privacy risk based on model size and data size.
Kind of, yeah. And the really important prediction from this scaling law is this. For models trained on truly massive data sets where you have a very high ratio of training tokens per parameter, the success of these loss-based membership inference attacks on an average data point basically drops to 0, or rather it approaches zero point 0.5 F1 score, which is just random guessing. Figure 15 shows this.
So for the giant models we see today trained on trillions of tokens, trying to figure out if some random sentence from the web was in its training data, just by seeing how well the model predicts it, that's basically impossible according to this.
For the average sentence, yes, that's what the law predicts. And they didn't just theorize, they tested this. They validated it on actual GPT-2 models, the 125 million and 1.5 billion parameter ones. And their scaling law held up pretty well. So this provides a solid capacity-based explanation for why many membership inference attacks just don't seem to work well against these huge models trained on web-scale data. The model has generalized so much that the signal for any average training point is drowned out.
Okay, so finite capacity, it forces generalization on big data sets, which hides the average training example from these kinds of privacy attacks. But the model does still memorize some things from real text, right? It just doesn't forget everything specific. So what kind of data points actually get stuck in its memory?
That's a great question. Because unlike the random data where memorization is pretty uniform until the capacity is full, on real text data, it's really uneven. Figure 16 shows this clearly.
Uneven, even after they try to remove duplicate data, like in FineWeb.
Exactly. Even in a carefully deduplicated data set, there's what they call a long tail. Some specific data points are way, way more highly memorized than the vast majority of others.
Okay, so is there a pattern? What makes a specific piece of text likely to be in that highly memorized tail?
Yes, they found a strong correlation. The most highly memorized examples strongly correlate with having high TF-IDF scores. That's Figure 17.
TF-IDF, term frequency inverse document frequency.
Right.
That measures how, like, unique or rare the words in a text snippet are compared to the whole data set, doesn't it?
Precisely. So text sequences that contain words or combinations of words that are very uncommon, very distinctive within the massive training set, those are the ones much more likely to get memorized compared to common sentences or phrases.
Can you give an example? What did they find when they looked closely?
Yeah, they did a manual check. Table 4 has some examples. They found these super memorized high TF-IDF snippets often included things like sequences of text from non-English languages, Japanese, Chinese, Hebrew, Greek phrases or sentences mixed into the primarily English data set. Actually, the single most memorized example they highlighted after deduplication was a sequence of Japanese words. The model could apparently reproduce it perfectly if you just gave it the first token.
Whoa, that's wild. So the model's limited budget for specific memories isn't just grabbing random facts. It seems to preferentially latch onto these statistically weird sequences, especially things that stand out linguistically, like bits of other languages, even if it's mostly trained on English.
It really suggests that those rare linguistic features, because they have such high TF-IDF scores, they just sort of pop out in the statistical landscape of the data, and they get disproportionately captured and stored in that limited specific sample memory, especially once the model has generalized all the common patterns and filled up its capacity.
Man, this has been a really fascinating deep dive. Okay, so let's just quickly recap the big takeaways for everyone. We've got this new way to think about and measure memorization based on compression, measured in bits per sample. Using that, researchers found a pretty consistent capacity limit for these models, around 3.6 bits per parameter.
Yeah, and hitting that capacity limit seems to drive this trade-off where models generalize better on real text but actually reduce memorization of specific samples.
Right, which gives us a really clean explanation for that whole double descent phenomenon.
Exactly. And understanding this capacity also helps explain why privacy attacks like membership inference are predicted to become ineffective on average data points for really large models trained on huge data sets.
And finally, the really surprising bit. What does get memorized tends to be statistically rare stuff, things with high TF-IDF scores, often including snippets of non-English text, even in mostly English training data.
It's definitely a powerful lens for looking inside these models. It helps us understand their behavior, their limits, and maybe think a bit more critically about the data we feed them.
Absolutely. And it leaves you with a thought, doesn't it? If these models, trained on these vast, diverse data sets, end up disproportionately remembering the rare, maybe non-English parts. What does that mean for future data sets? And what kinds of weird skills or maybe even subtle biases might models pick up because these statistically unusual inputs stick in their memory more strongly than the common patterns? It makes you wonder about the hidden ways the data landscape shapes what the model actually learns and retains.